Hello, everyone. In this last week of class, we will be discussing a bit of rudimentary probability. We're going to start in 8.1, which discusses properties such as the fundamental counting principle and permutations, and then move up to 8.4, which gets into some basic elements of probability. And like with chapter 7, we're not going to be doing the whole chapter, but we're just setting it up so that to give you kind of the tools and the basic ideas to make sense of the rest of the chapter. And in the latter half of chapter 8, it gets into more advanced probability theorems such as Bayes theorems. And I suggest that if this is a subject that interests you, that you read a little bit more and do study a bit further outside of just what we're doing in our class. But anyways, let's begin with the first section, which is on the basic counting principle, or in other texts I've used, sometimes it's referred to as the fundamental counting principle. So it's an idea that, well, let's just go ahead and read it. It says, suppose that a procedure involves a sequence of k stages. Let n sub 1 be the number of ways the first stage can occur, n2 be the number of ways the second can occur, and so on. It says then the total number of different ways the total procedure can occur is n1 times n2 times etc. Or essentially that it's saying is if I'm trying to run an experiment where let's just look at the example number 1. Let's say that Linda took 4 blouses with her and 3 pairs of pants with her on a work trip, denoted by the color of each one, so we can distinguish each blouse and each pair of pants. And it asks, assuming complete compatibility, meaning that she could pair an orange shirt with tan pants or a red shirt with white pants or something, and while we're just going to ignore, fashion and just pretend each one of those colors is compatible because I really don't know any better at the end of the day. Basically, what the question is, how many different outfits could she make? Um, and the point I'm trying to illustrate is this is actually very easy to figure out if we use the fundamental counting principle and the idea of permutations. But we'll get to all that in a minute. And then it says write them out as a sample space. And what if she also brought 2 pairs of shoes? But before doing anything else, we can always solve these sorts of problems by method of exhaustion, or basically by making a graph or kind of just outlining what are all the outcomes. But the point is that in more complex problems, it might be impossible or take way too long to try to figure them out by literally laying out all the options. So we're trying to set up some ideas that help us to solve more complex problems. But basically, we could figure out all the combinations, and actually, the term combination is specific in math, which is actually we're going to talk about what the difference between a combination and a permutation is, and how do we know which uh, formula to use in a little bit, because that's something that is that's very easy to mix up. But we could just write out all of the outfits. So she could pair up an orange blouse with a tan pair of pants. So we could write that by kind of just pairing it up by writing out the letters of those things using just OT. Or, another way that people will often write the combinations is, well, she could start with an orange shirt and then pair that with the tan pants, or she could pair the orange shirt with the black pants, or the orange shirt with the white pants, right? And that would give us 3 unique outfits. And each of the lines we could view as a representation of a particular outfit. But she could also choose to wear the green shirt, and in the case where she does wear the green shirt, it could be a combination of either she could use green plus tan, green plus black, or green plus white, and so on. Right? We could keep, illustrating these pairings by using a graph. Let me move myself over there. Okay. And so on, right? We could do the red pairings. Red could be paired with tan, red with black, red with white, or purple with tan, purple with black, or purple with white. And what we could do is then say, well, that's all of the pairings, right? Because we paired every single shirt with every single pair of pants. And we could kind of view this as, well, we could count the number of lines that I drew, which represents the number of unique outfits. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. And our answer to the original question is, she could make 12 outfits on her trip, and be able to dress differently without needing to, use unique things every single time. But basically, so how does this illustrate the basic counting principle? But if we view it a little bit differently, we could view the first event as selecting a blouse, to which there's 4 choices, and then the second event as selecting a pair of pants, to which there's 3 choices. And notice that if I just take 4 times 3, right, 4 times 3, um, that would give me 12, not coincidentally. And if we kind of examine our graph and look at, well, why is the fundamental counting principle true? Well, if I start with 4 choices, right, and I'm allowed to pair them with any number of things from the second choice, well, the first choice will lead to 3 choices, and each one of the options from the first choice will stem into that many objects. And so what we have is 1, 2, 3, 4, and it multiplies by 3, right? Because each choice has branches to each of the following choices. Or more simply stated, right, it's always just a product of the number of choices. So we give her 12 total outfits. And then the second part of this question, it asks, well, what if she also brought 2 pairs of shoes? Let's just say shoe 1 and shoe 2, or, whatever. You could put colors or whatever to them. But basically, that would multiply again, and it would stack like it would be 4 times 3 times 2. Or let's say she brought 7 pairs of shoes. It would be 4 times 3 times 7. Basically, you're multiplying the number of options together and assuming compatibility. If there's certain outfits that aren't going to work, obviously that would eliminate some of the choices. But if there are no restrictions to all the ways that we pair them together, that's always going to give us our outcome. So that would just be 4 times 3 times 2, which would be 24 options in that particular case. Or you could kind of imagine as, well, also we could pair it with shoe 1 and shoe 2, and then we could kind of view, well, each one of those stems would create more stems, and it would double the number of outcomes at the end of the day. So also it says to write a sample space, and if we're wondering what does that mean, but basically it's just in chapter 8 that gets into a lot of lingo which is more formalized for probability, basically using set theory and so on. So it's kind of important to just kind of understand what that means. But a sample space is just basically a set which lists the all of the options and all of the outcomes in a set form. So like I said kind of before, we could describe one outfit as OT, right, which would be orange shirt with tan pants. Or we could write it as, OB, OW. And basically, I'm just writing a mathematical set that includes all of the outfits where there's some sort of meaning to what I'm writing in there, often denoted by letters or numbers, depending on the context. Or you could list it as orange, tan, but, obviously we're using abbreviations, and I chose colors for the example that made it so there was no duplicates. But like say that there was blue and black, then you'd have to obviously differentiate B from B. But often also subscripts are used to differentiate, say, shoe 1 and shoe 2 if we don't have different colors on them. But basically, if we finish this list, right, we could list every outfit combination. And again, the word combination has a specific meaning mathematically, which doesn't necessarily make sense in this particular problem, and we'll get to that. But anyways, we could do green with tan, GB, GW. There could be RT, RB, RW. And I'm just writing out everything that I drew in the graph, but it's just writing it in a different form. And as a sample space, it's just using mathematical sets. And so, the book will be using that quite a bit, and it's kind of important just to understand what it means in that setting. So let's do another example. Let's say in a board game, a 6-sided dice is rolled, die, singular for dice, and 2 coins are tossed. Write the outcomes as a sample space. Okay, so with coins, usually we write it as heads or tails. So the sample space would consist of outcomes. Well, we could start with a 1. So it could be 1 head, right? Or it could be 1, whoops. Or we could start with a 1 and then a heads and a tails, or a 1 and a tails and a heads. But basically, in order to think of the possibilities, we could kind of just list them all until we make sure to measure them out. And there is a mathematical way that we can calculate how many outcomes there would be, which is the math behind permutations. And we'll get to that in a minute as well. But if you're a little bit stuck on how to get started, you could always just start writing your possibilities to try to understand it a little better, right? And so if in this list of outcomes, if I started with a one, I could think about then, well, what are the other ways that could happen after I toss the coins? But basically, we could do two heads, two tails, a heads then a tails, or a tails and heads. Um, and you might be wondering, well, is one heads tails different than one tails heads? Because really it's one heads and one tails, and that really depends on the context. Because in some games, the order that you flip them might matter, and in others it might not. So, and that this is really the difference between a permutation and a combination, and we're going to get to that. But in the case of this, we would treat them as different events in the sample space. And each element of the sample space, which is separated by commas, is treated as a unique event. And in some contexts, you might not treat these as unique events, but again, that would just depend. Um, I would still consider them as unique events because they're different, but in terms of probability and sometimes the difference in the events might not make a difference if you see what I'm saying. But anyways, then additionally, we could do the same thing where we had two heads, right? If it started with a two heads tails, two tails heads, and two tails, and so on, right? We could then have three, and then four, and so on. Or, we could just do it mathematically, because to roll a dice, a standard six-sided dice, there would be six outcomes. Then flipping a coin, there's two outcomes. And if we're flipping two coins, it would just be 6 times 2 times 2. And if we wanted to know the total number of outcomes, that should be also 24, coincidentally, to the problem above, which is just 12 times 2. Or as I can see by starting to list the sample space, and by writing ... here, let me write it a little bit better. But I'm kind of implying that, I'm just too lazy to list the rest of the sets. But, if I was trying to write the full sample space, I would want to keep going and do the same for 3, 4, 5, and 6. And a lot of times you can use a spreadsheet like Excel to build your sample spaces and kind of get a better visualization of what's going on in the particular problem. But I could kind of confirm with thinking about it and just the math behind the fundamental counting principle, yeah, there would be 4, 8, 12, 16, 20, 24 total outcomes if I were to list them all. And just in doing one more example before I wrap this video up, it says a subset of the example space is called an event. Assume that in testing the board game, you want to know the event in which the player rolls at least a 5 on the die and at least one heads on the coin. And it says then to describe as a set. So there are actually various different ways to do these calculations and figure out how many of these options there are. But if you know the entire sample space, finding an event is pretty easy from there. So, like, basically, we want to know what are the outcomes which the player rolled at least a 5 and at least one heads. Well, if we're kind of comparing our sample space, since I didn't finish it, it's a little bit, not perfect. But if you pretended that these were 6s and 5s, I could see, well, there's the case when the player could roll a 6 and then one heads, one tails, or a 6 and a tails and a heads, or a 6 and two heads. So like these three possibilities satisfy the second condition that they have at least one heads, but if it was a double tails, it would not be satisfied. So it reduces this option, of these four possibilities down to just three, because really only 3 out of the 4 times are you gonna get at least one heads. And you can reduce this to more basic probability, and that's all what we're going to get to in section 4. But it could have also been a 5 heads tails, 5 tails heads, and 5 heads. And that should be our entire event. Basically, and the book often will use capital E to represent an event happening. But basically, it's just a subset, meaning it's like part of the larger set, but not all of them. Well, technically, a subset could be the entire original set, which is the difference between what we call a proper subset and just a general subset. But I don't think it's worth really worrying about all of the notation and those details. But anyways, we see there are 6 possible events in the sample space, and we'll get back to probability and how this all relates to it later. And then the last question on the first page of the packet, it says a multiple choice exam consists of 20 questions, each with 4 choices. So, like a test would be A, B, C, D, typically. And let's say you have no idea about any content of the test and you're just going to randomly guess questions on the test. How many different ways could you guess your way to answering that test? And so basically, well, if we think about using the fundamental counting principle, well, if I'm thinking about question 1, right? Question 1, there are 4 choices. And then I could think about question 2, well, there's also 4 multiple choice test questions. And question 3, there's going to be 4 choices, and so on, right? There's always going to be 4 choices up until question 20, which there are also 4 choices. And what we would need to do is just take the product of each one of those numbers, because if I'm thinking about each question as an individual option in this chain, basically it's a procedure involving 20 sequences or 20 stages, and each stage has 4 potential ways of answering it. Well, if I just took 4 times 4 times 4 times 4 times 4, or that would just, as another way of writing it, would be 4 to the 20th power, would be the number of ways I could run through the test, right? And if I was to list the sample space, I wouldn't really want to, because that would be absurd. But I could answer every single question A all the way through, or B B B B B B B C C C C, or A B C or whatever. Thinking about all the it's enough to make your head spin, but we can quite simply and very easily figure out that number by an exponent. And this is how exponents fit into probability, and they're very common objects within a probability problem. But if I take 4 to the 20th power, that would be a massive, massive number. Basically, I'll write approximately because my calculator didn't even give me the full number, but it's about 1.0995 times 10 to the 12th power. Because remember that this E means scientific notation. Or, that would just mean I need to move that decimal place 12 spaces. So 10995. So I'm going to have 12 digits after that decimal place. Or it's in the scale of millions, billions, trillions. So it's over 1 trillion possible ways of answering that test. Which is why, multiple choice tests can be argued that that they really do test your ability, because a lot of times people will claim that multiple choice tests are not really a very good judge of understanding of the content, because you can just randomly guess and get some of the questions right. But really what this exemplifies is that in a 20 question test, there's literally a trillion different ways of answering it. So the chance that someone would answer them all correctly is very, very low. And we'll come back to probability in a minute, but obviously there's other techniques for working with multiple choice where you can kind of whittle away some of the answers using a basic strategy, which can often help. And I mean, as a mathematician, I don't really like multiple choice tests because I don't get to see, I don't, you're graded on just the answer, but not really the process. And in math, we know that the process is more important than the answer, because if we don't know how to progress through a problem, if we don't know the process, the answer is not really worth anything, because we're not really understanding the procedure in which we use math to solve problems, and that's what's most important. So that's why, when I grade, I'm usually focused on the steps. And even if there's a small mistake getting to the right answer, I try to give you a grade based on whether you understand the material and you understand what mathematical procedures do. Anyways, I'm getting off topic. Let's wrap up this video. In the next video, we'll discuss the concept of permutations, and then we'll work on into combinations and eventually into how these all play into probability.